All right, so I'm first going to say a little bit more about tangent vectors. It's like viewed as directional derivatives. It's like and how they change under changes of coordinates, right? So if you recall, it's like if you have two charts, so sort of tangent vectors under changes of coordinates, right? So if you're given two coordinate systems, sort of coordinate charts, uh, let's say cos Ci, and this, right? Then you have two basis elements. Um, so that's okay. So all right. So you have the partial derivative with respect to cos Ci, and I want to ask, and there are partial derivatives with respect to this other coordinate system as well. So how are these related to each other? How do you go? So how do you go from this to this, right? So that's the basic question. You're given two coordinate charts, it's like on the manifold, and you have sort of a basis, it's like for the tangent space, it's like associated with each of the coordinate charts. How do you change between this, right? So, and if you recall, it's like the way to think about this is in terms of directional derivatives. It's like a scalar value functions. So essentially what is going to happen is that you're going to think of a function which is defined on the manifold M, right? So there's a map M, it's like F, it's like to the rails, right? And if you recall, it's like you have two coordinatizations of F by using it's like the two charts which are given to you, and then you differentiate respect to the components. That's really what's happening here. And you want this kind of construction to be independent of F, basically, right? So what ends up happening then is that if you okay, if you look at one of these directional derivatives with respect to the first coordinate chart, right, then it's going to be related to some linear combination, it's like of the basis for the tangent space with respect to the second coordinate chart. As you might expect, both of these coordinate charts induce bases for the tangent space, so you should be able to write any tangent vector as a linear combination of tangent vectors in the other basis, right? So it turns out that this thing is going to be related to the Jacobian of this transformation between the coordinates, right, in this way. And then similarly, if you wanted to go from this basis to the first basis, you can do so as follows. Okay. All right, and then here it's like you have this repeated index thing. It's like which we've seen before. This there's an implicit sum over k and there's an implicit sum over I via this Einstein summation convention. And then these are basically Jacobians of the transformation between the two coordinates. So I'd linearize, it's like the map, it's like between the coordinates at the point which I care about. And then okay, so with that, yeah, so with that, it's like you can tell it's like how the basis transforms, and in particular, it's like how the a representation, it's like of a tangent vector, it's like transforms under a change of coordinates, if you will. Okay, so more generally speaking, it's like this falls into the sort of the abstract discussion we had earlier about the tangent lift. It's like of maps between manifolds, right? So here, the change of coordinate maps is just a it's a map. It's like in some sense on the manifold. Yeah, but anyhow, so this is just how you might go about taking a tangent vector. It's like which was written. It's like with respect to one coordinate representation, induced. It's like by one of the coordinate charts to a different representation, right? And so once you know this, it's like you can then figure out how the tangent vectors, yeah, change more generally speaking. Okay. All right. So let me stop here for now.